Hi everyone, my name is Neha Kadam, and in this lecture we are going to learn about encoder and decoder in detail. So let's get started. Here you see the block diagram of an encoder. Encoder is a digital circuit that produces a binary output code depending on which of its inputs are activated. So here these are the inputs starting from A0 to A7, and these are the three outputs. So let's see next. Only one input is activated at a time, and then binary code is produced at the output side. And this is the IC form. These encoders, they are available in the IC forms, and you will get to see them in the lab experiments. And then we have a decoder. So this is the block diagram of the decoder, which has these three inputs, and then these are the outputs. So decoder, it is a digital circuit which converts an input binary code into a single numeric output. Okay, so you send the binary code from here, and then you will have a decimal number or decimal output you will get at the output side. So binary code input is given and only one output activated at a time. Now we're going to start with the decoders. So let's read the definition of decoders here. A combinational circuit that converts binary information from n coded inputs to a maximum 2n coded outputs. So it is like n to 2n decoder, and examples are 1 to 2 line decoders, 2 to 4 line decoders, 3 to 8 line decoders, and so on. There is another definition of a decoder which I would like to mention here, that a decoder is a circuit which changes a code into a set of signals, and it activates one or more circuit output upon detection of a particular digital state. So in short, you can say that decoder basically decode the coded information from one format to another format. Okay, so our one format in which it takes it as an input is your BCD, and the output format is decimal. Now let's see next. Now next is the is an example of the decoder where the BCD input is connected to the decoder driver, and then further it is connected to the 7-segment display. So you can see here right now the BCD input is 0100, which is 4 in decimal, and that's what is shown over here in the 7-segment display. So this is just an example of a decoder. Now we are going to see different types of decoder. So let's begin with 2 to 4 line decoder. Here you see these are your input A1 and A0. These are the two inputs, and then D0, D1, D2, and D3 are your outputs. So these are the 4 different combination input can have as a BCD. So when it is A1 and A0, A0 or A0 is they both are 0, then the output will be like this. D1 will be activated and rest of them will be deactivated. And when you have 0, 1, then in that case D1 will be activated and then rest of them will be deactivated. And when you have 1, 0, then D2 will be activated, and when you have 1, 1, D3 will be activated. Okay, so this is the truth table for 2 to 4 line decoder, and here on the right you see the logic circuit for a decoder. So you see these are the two inputs going, A0 and A1, and to show the 0 and 0, or to send that 0 input, we have this NOT attached here. So right now here you have like 1, and when it goes through this inverter or NOT gate, you have 0 here. Okay, so we know that when D0 is 1, at that time you have A1 and A0, they both are 0, which means they both are in bar or complemented. So you see this is one AND gate represented for D0, and D0 is equals to A1 A0 bar, and that's why you have these A0 and A1 bar, they are going in to the AND gate. And then you have D1. So D1 is activated when A1 is bar or 0 and A0 is 1. Okay, so that's why you have A1 bar A0. And then you have, when your D2 is activated, at that time A1 is 1 and A0 is 0. So A1 A0 bar, so that's what you have here. And then when D3 is activated, they both are 1. So that's why you have A1 A0. Okay, and then for each of them you see that they are forming an AND gate. So that's why you have like 4 AND gates, and then based on that the input is going. So you have A1 A0 which is going into this AND gate, and then here it is going A1 and A0, and then in this one A1 bar and A1 bar dot A0. So this is 2-to-line decoder. Now let's see 2 to 4 line decoder with the enable. So you see here we have this enable, another input which is going in here like this. So this is the same circuit, rest except the enable, rest of the circuit is same here. Okay, the logic circuit is same, and the boolean, the truth table is also same. Now what is the benefit of adding the enable? So you see that when enable is 0, okay, when enable is 0, then if you give any input like this, X is representing either 0 or 1. So whatever input you give, it will not matter, your output is going to be 0. So do you understand? Like if enable is 0, then it will make all the output 0, and it will not care about what the other input is going into the D2. Okay, and you can do the math also. If this is 0, which means if 0 signal is going in, then whatever the input you are going into these AND gates, it's going to be 0. Okay, so to make it simple, to turn it off the circuit, we use this enable. So if you just just send 0, you know that your circuit will be off and you will get just all zeros. Okay, so that's why we have this enable, and along with enable we have these don't cares. So these X are called your don't care. It can be 0 or 1, it doesn't matter, and that's why it is don't care. And then rest of the truth table is same. So when the enable is 1, then only it will respond to the output, otherwise it will not. So this is the function of enable, and this circuit and the truth table represents the 2 to 4 line decoder with enable. Now we have 3 to 8 line decoder, so which means we have 3 number of inputs and 8 number of outputs. So you see here these are the inputs, different combination of binary for 3 inputs, and then these are the outputs generated for these 3 inputs. So when this is for first case, when all 0, at that time D0 will be activated, and when A0 is 1, at that time D1 is activated, and when it is 2, or you can say like 0 1 0 is basically your 2. When it is 2, then at that time D2 is activated. When it is 3, 0 1 1 is 3, then D3 is activated. When it is 1 0 0, which is 4 in decimal, then your D4 is activated. When it is 5 1 0 1, which is 5, then your D5 is activated. And when you have 1 1 0, which is 6, then your D6 is activated. And when you have all 1, which is 7, then your D7 will be activated. So that's how you form the truth table in a 3 to 8 line decoder, and rest of them will be 0. And on the right hand side you see the logic diagram for this type of decoder. You see that 3 inputs are going in, and then we also need like a NOT gate to have like 0 input, or A2 bar or A1 bar or A0 bar. So that's why we have these NOT gates here, and then the rest of the circuit is same to the previous circuit. I'll pick a few outputs and tell you like how they came out. So for example, D0, you see here D0 is activated, it is 1 when all the inputs are 0, and that's why you have A2 bar, A1 bar, A0, they represent 0 0 0. Let's pick D3. When D3 is 1, at that instance you have A2 0, A1 1 and A0 1. Okay, so that's the same thing. So it should be A2 bar A1 A0. So that's what you have here, A2 bar A1 A0. And then let's see for D7, A2 A1 A0. So D7 is this, and you see corresponding to this we have all of them are 1, and that's why you have A2 A1 A0. And let's pick one more for D5. D5, let's see here, it is 1, so you should have A2 A1 bar and A0. So A2 A1 bar and A0. So that's how this Boolean expression has come out for each AND gate, which represent your output. So this is your 3 to 8 line decoder, and I would advise you to make this logic circuit on the notebook, so that you have a practice of how this logic diagram can be made from a truth table. Now next is the electronic encoder. So encoder is a digital circuit that performs the inverse operation of a decoder, and an encoder has 2 N input lines and N output lines. The output lines generate the binary equivalent to the input line, whose value is 1. So this is your encoder. And another definition of encoder is that it is the process of converting the signal message into a coded one. And an encoder, it has like 2 N input lines or inputs and N number of outputs. So output in this case is going to be binary value of the selected or active input, and that's what we are going to see next. So before we get into the encoder truth table logic diagram, let's first see here one example of encoder where it can be used. So you see this is a keypad connected to the encoder IC, and encoder IC is connected to the BCD output, and this output display could be any LCD LED. So or VF display it could be. So if you press any of the key, you will get corresponding binary coded value. So for example, in this particular case we have 3, and the binary conversion of 3 decimal is 0011. So this is an example of a encoder which converts decimal to binary. Now let's see 4 to 2 line encoder. So this is a 4 to 2 line encoder. So you see these are the inputs D0, D1, D2 and D3, and it is generating 2 outputs Q0 and Q1, and this is the truth table. Okay, so when your D0 is activated, when you send 1 to this data input, at that time the output is 0 0. And when you send D1 as 1 and rest of them are 0, like when you send the input through D1, at that time output will be 0 1. And when you send D2 as your input and then rest of them are 0, then in that case it is 1 0. And when your D3 is activated, then your output is 1 1. Okay, and then when all the inputs are 0, then output will go, it doesn't matter whatever is your output, it does not matter. Okay, so it will so in this case also you can again use the enable to to show that like if it is all 0, then there should be no output, and it should work only when you have 1. Okay, so logic expression. So if you see Q1, so you know that how to build the logic expression and reduce it. So let's see for Q1. So we will check for ones. Where are the ones? So we see 1 here and we see 1 here. So corresponding to that, we will see where it is 1. So when D2 is 1, then Q1 is 1. When D3 is 1, then Q1 is 1, and that's why you have Q1 is equals to D2 plus D3. And the same we will do for Q0. Q0 is 1 here, which means at this point D1 is activated, so that's why you have D1 here. And then we will go down and we will see that Q0 is activated at this point, and at this point D3 is activated, so that's why we have D3 here. Okay, so you understand like how the logic expression has come from the truth table. And next we are going to see the logic diagram for this particular case. So based on this, you can build the logic diagram. So you understand that these are the two outputs, and they have a plus sign here, where these are the two inputs to each of these output, which means it is forming an OR gate, and that's why you have two OR gates, and one in one of the OR gate your D3 and D2 will go, which will produce Q1, and then in another one you have like D3 and D1, and you have output Q0 is generated. Now next is 8 to 3 line encoder. So you see here we have 8 inputs going into the encoder, and then 3 outputs are coming out. So if you look here, it says priority encoder. So this term priority encoder we are going to learn after this slide. So just for now, understand that 8 inputs are going and 3 inputs are coming out. And this is the truth table when you know that previously how each time one of the input will be turned on. So that is same here. D0 is 1, D1 is 1, D2 is 1, and then so on, and these are rest of them are 0. And these are, for now, understand they represent the don't care, but we are assuming that these all are 0. Okay, and corresponding to that we have output generated. So when D0 is 1, at that point all outputs are going to be 0. Okay, and when D1 is 1, then you will have 1 here, 0 0 1, and then when D2 is 1, then you have 2 decimal here. D3 is 1, you have 3 decimal here. So I'm just converting like this is a binary 0 1 1, which represents your 3. Okay, and then you have D4, which shows here as 4, 1 0 0 is 4. And then D5 is your 101, which is 5, and then D6 is 1, so which is 110, and decimal is also 6, and D7 is 111, which is decimal 7. Now again, the way we did it in the previous slide, which was 4 to 2 line encoder, same way we are going to do it here. We know that these are the 3 outputs, Q0, Q0, Q1, Q2. So we will see how we can generate the logic expression. So for Q0, Q0 is here. We see that Q0 is going 1 4 times. So here it is going 1, and then here, and then here, and then here. Okay, so corresponding to that we will see what input we have. So when it is 1 here, it is 1 at D1, and it is 1 at D3, it is 1 at D5, and it is 1 at D7. So that's what you see here, D1, D3, D5, D7. Same we are going to do it for Q1. We will see that where are the ones. So we have 1 here, 1 here, 1 here, and 1 here, and we will ignore zeros. So corresponding to that, whatever input is activated, we will write that. So we have D2 here, and then D3, and then here D6 and D7. So D2, D3, D6, D7, and same with Q2. So you know that on the top all are zeros, and at the bottom all are 1. So we are going to have D7, D6, D5 and D4. So that's what we have here, D4, D5, D6, D7. Now if you look carefully at these logic expression, you will get to know that they are using the OR gates, right? Because if we see the addition sign here, so which means we have to make the OR gate. So for this particular case, we will have 3 OR gates. Q0, Q1 and Q2 are going to be our OR gates, and D1, D3, D5, D7, this is going to be input for this Q0 OR gate, and then these 4 are input to this OR gate, and same with Q2. Now this is the logic diagram you see here. So we have Q0 here, Q1 OR gate, and then Q2 OR gate. Each of them will have 4 inputs. So let's check one by one. Let's start with Q2. Q2 has D4, D5, D6, D7. So you see that D4, D5, D6, D7 all going into the OR gate. And then we have Q1 which has D2, D3, D6, D7. So D2, D3 is here, and D6 and D7 input has been taken from here. Okay. And then we have Q0, which is D1, D3, D5, D7. So D1 is going in here, and D3 has been taken from here. And then we have D5 taken from here, and then we have D7 taken from here. Okay, so that's how you form the logic diagram for 8 to 3 line encoder. Now let's see next. Now encoder, there are some issues with the encoder design which we saw previously, and there are 2 ambiguities associated with the design of a simple encoder. First is only one input can be activated at any given time. If 2 inputs are activated simultaneously, the output produces an undefined combination. So for example, if D3 and D6 are 1 simultaneously, the output of the encoder will be 111. So let's see, let's go back again. So D3 and D6. So D3, so this is our D3 and D6. So if both of them are going to be turned on at the same time, then what will happen? So right now we know that each time we are sending one input at a time. Okay, so right now D0 is activated, and then D1 is activated, and so on. But now it is saying what will happen if for example 2 inputs are on. So for example, D3 is sending the input, and at the same time D6 is also sending the input. Then how your output is going to detect like which output it should generate corresponding to whether it should generate the output based on D3 or D6. So in that situation your output may get confused, and that's why we have these priority encoders. Now let's read the second point. An output with all zeros can be generated with all the inputs are zeros, or when D0 is equals to 1. So let's see. So let's one more time I'm going to state this that we need priority encoders because there were some shortcomings of the previous encoder circuit, because it was generating wrong codes. It can generate wrong codes if more than one input is active at the same time. So to avoid that problem, the solution is to define the priority level to each input. So in case if 2 or more if 2 or more inputs are active, then make the output code corresponding to the highest priority input. So I am emphasizing this again, that the solution for this type of issue is that if there are 2 inputs activated, then make the output code corresponding to the highest priority. So you have to define the highest priority. So let's see, solves the priority encoder solves the ambiguities mentioned above, which we saw in the previous slide. Multiple asserted inputs are allowed. One has priority over all others. Separate indications of no asserted inputs. So this priority encoder, this outputs priority encoder's output corresponds to the whatever the currently active input is, which has the highest priority. So when the input with the highest priority is present, then the other input with lower priority will be ignored. So let's see that. So through this circuit, we will see how priority encoder is working. So we have so this is 4 to 2 line priority encoder, and you see here when all are 0, then it doesn't matter what output is, because we have used the enable here. So V is representing here for enable. So if enable is 0, then it doesn't then your output is going to be whatever output going to be, it will assume that your input is 0. Okay. And when enable is 1, okay, then only it will work. So when it is 1, so you see here D0 is 1, then it is sending 0 0. When D1 is 1, and now notice in this third line of the truth table that D1 is 1 and D0 is X. So this X represents don't care, which means whether this is going to be 0 or 1, it does not matter, because what matters is the second second column's value. So in this column you see that D1 is activated. So this D1 is at a highest priority compared to the D0. So if D1 is activated, then output is going to correspond to D1 only. It will not look for D0. And the same is for the third case, when D2 is 1 and D1 and D0, it will not care whether they are 0 or 1. It will give the output corresponding to D2. And same with this one, when D3 is activated, it will not care for the input being sent through D0, D1 and D2. So your output is going to be correspond to D3. So this is your priority encoder. You use these don't care, which will avoid that problem. And then this is the logic diagram. So you can make the logic diagram again. You have to so in this you have outputs, 2 outputs, and then you have the enable. So by this time now you must be more experienced how to make the logic diagram. So I would request you to make your own logic diagram for this particular case. And so let's see these points. So if 2 or more inputs are equal to 1 at the same time, the input in the highest numbered position will take precedence. So we saw that a valid output indicator designed by V, which is enable, is set to 1 only when 1 or more inputs are equal to 1. So V is equals to D3 D2 plus D3 plus D2 plus D1 plus D0 by inspection. So that's what you see here is going in, is equals to V, which is your enable. And a rest of this circuit is pretty easy. A0 and A1 we are using OR gate, and this is also OR gate. This logic gate diagram is a little bit has problem here, but this is assume that this is a OR gate. Okay, and then we have AND gate here, and then we have a NOT gate here, and that's how your input is going. So you can make the logic diagram considering that what are the inputs are here, and then based on that you can make the logic circuit. So this is the this was the last topic of this lecture. So thank you so much for watching.